In this outcome, we look at how a material's structure decides its properties, working through ionic, metallic, macromolecular, and simple molecular types, and the remarkable allotropes of carbon. Let's begin. The big idea here is simple but powerful. The way particles are arranged and bonded controls how a material behaves. Melting point, hardness, electrical conductivity, all of it traces back to structure. There are four main types to keep in mind: ionic, metallic, macromolecular, and simple molecular. And here's a striking fact: the very same element can give completely different materials, as the allotropes of carbon show. Our job is to predict and explain properties from the structure, which is exactly how you choose the right material for a job. Some terms to have ready. A lattice is a regular, repeating, three-dimensional arrangement of particles. An electrostatic force is the attraction between opposite charges, such as a sodium ion and a chloride ion. A delocalized electron is one that's free to move, not fixed to a single atom. An intermolecular force is a weak attraction between whole molecules. And an allotrope is a different structural form of the same element. Let's survey the four structure types. Ionic is a giant lattice of oppositely charged ions. Metallic is positive ions sitting in a sea of delocalized electrons. Macromolecular, also called giant covalent, is a huge covalently bonded network. And simple molecular is small molecules held together by weak forces. The idea to hold on to throughout is the contrast between the strength of bonds within particles versus between them. Strong bonds all the way through means a high melting point. Let's compare ionic and metallic. Ionic structures form between a metal and a non-metal, sodium chloride and magnesium oxide, for instance. The ions are held by strong electrostatic attraction. They conduct only when molten or aqueous, and they're hard but brittle, shattering when the layers shift. Metallic structures are made of metal atoms: copper, iron, aluminium. They're cations in a sea of delocalized electrons. They conduct as both solid and liquid, and they're malleable and ductile, because the layers can slide. Looking at ionic structures more closely, they form a giant lattice, with each ion surrounded by ions of the opposite charge. Those strong forces give high melting and boiling points. In the solid, the ions are fixed, so there's no conduction. But molten or dissolved, the ions are free to move and carry charge. They're brittle because shifting a layer brings like charges together. Sodium chloride is the classic example, melting at 801 degrees and readily dissolving in water. Let's explain sodium chloride's behavior in terms of structure. Why does it melt at 801 degrees, yet only conduct when molten or dissolved? Sodium chloride is a giant ionic lattice of sodium and chloride ions. Each ion is strongly attracted to 6 oppositely charged neighbors. Melting means overcoming a great many of these strong electrostatic forces, which takes a lot of energy, hence the high melting point. In the solid, the ions are locked in place, so charge can't flow. Only when molten or dissolved are the ions free to move towards the electrodes, and that's when it conducts. Now, metallic structures. You have a lattice of positive ions in a sea of delocalized electrons. Those mobile electrons carry charge, making metals good electrical conductors, and they transfer heat efficiently too, so metals are good thermal conductors. Layers of ions can slide over one another without breaking the bonding, which makes metals malleable and ductile. And strong metallic bonding gives generally high melting points. Copper is the everyday example, used for wiring and pipes. Let's explain why copper can be drawn into wires and conducts electricity. Copper is a lattice of copper ions surrounded by delocalized electrons. When you apply a force, layers of ions slide over one another, and the electron C keeps the metal held together as they move, so it's ductile rather than brittle. Apply a voltage, and those delocalized electrons drift through the lattice. That drift of electrons is precisely an electric current. So sliding layers explain the ductility, and the mobile sea of electrons explains the conduction. Macromolecular, or giant covalent, structures are next. Here, millions of atoms are joined by strong covalent bonds into one continuous network with no separate molecules at all. That gives very high melting points, since bonds must be broken throughout the whole structure. They're usually hard and insoluble in water, and usually non-conductors because there are no free charges. The standard examples are diamond and silicon dioxide, SiO2. Simple molecular structures are the opposite in feel. Each molecule is small, with strong covalent bonds inside it, but only weak intermolecular forces between the molecules. So they have low melting and boiling points because those weak forces break easily, and many are gases or liquids at room temperature. They don't conduct, having no ions or delocalized electrons. Carbon dioxide, iodine, water, and oxygen are all good examples. Let's contrast these two directly using silicon dioxide and carbon dioxide. Silicon dioxide is a giant network of silicon-oxygen covalent bonds. It melts near 1710 degrees. It's a hard solid, insoluble, and non-conducting, and it's what sand and quartz are made of. Carbon dioxide is separate O double bond C double bond O molecules. It sublimes at -78 degrees and is a gas at room temperature, with only weak forces between the molecules. Same kind of bond, but wildly different behavior, all down to the structure. Let's work that comparison through. Both contain covalent bonds, yet silicon dioxide is a hard solid and carbon dioxide is a gas. Why? In carbon dioxide, strong carbon-oxygen double bonds hold each small molecule together. But between the molecules, there are only weak intermolecular forces. Very little energy is needed to separate them, so it's a gas at room temperature. In silicon dioxide, by contrast, every silicon and oxygen is locked into one giant covalent network, and melting it means breaking many strong covalent bonds, giving a very high melting point. It's the structure, not the type of bond, that differs. Let's check your understanding. First, why does an ionic solid not conduct, but its molten form does? Second, explain, in terms of structure, why metals are good conductors. And third, predict whether a substance that melts at -40 degrees is giant or simple molecular. Have a think before we continue. Now for one of chemistry's best illustrations of our theme, the allotropes of carbon. Allotropes are different structural forms of the same element. Carbon forms diamond, graphite, graphene, and the fullerenes, and although every one is pure carbon, their properties differ enormously. What changes is simply the arrangement of the atoms. It's a superb demonstration that structure controls properties, and it all hinges on the fact that each carbon can form up to 4 covalent bonds. Take diamond first. Each carbon is bonded to 4 others in a tetrahedral network, making it a giant covalent macromolecular structure. That rigid 3-dimensional framework of strong bonds makes diamond extremely hard. It has a very high melting point, subliming above around 3550 degrees. And because every outer electron is used in bonding, there are no free electrons, so diamond is an electrical insulator. Its uses follow from its hardness, cutting tools, drill bits, and abrasives. Graphite is pure carbon too, but arranged quite differently. Here, each carbon is bonded to only 3 others, forming flat hexagonal layers, which leaves a 4th outer electron per atom delocalized between the layers. The layers themselves are held together only by weak forces, so they slide over each other easily, making graphite soft and slippery, useful as a lubricant and as pencil lead. And those delocalized electrons mean graphite conducts electricity, which is why it's used for electrodes. Let's put diamond and graphite head-to-head. Diamond has 4 bonds per carbon in a tetrahedral 3-dimensional structure. It's very hard and rigid. It does not conduct because there are no free electrons, and it's used in cutting and drilling tools. Graphite has 3 bonds per carbon in flat layers. It's soft and slippery because the layers slide. It conducts thanks to 1 delocalized electron per atom, and it's used in electrodes and lubricants. Identical atoms, opposite characters. Graphene is a wonderful modern material, essentially a single 1-atom-thick layer of graphite. It's a hexagonal sheet of carbon, each atom bonded to 3 others. It's exceptionally strong for its weight and an excellent conductor because electrons are delocalized right across the sheet. It's also almost transparent and very light. Those properties make it valuable in flexible electronics, composite materials, and sensors. Fullerenes are another family, carbon atoms arranged as hollow cages or tubes. Buckminster fullerene, C60, is a ball of 60 carbon atoms. Fullerenes are simple molecular, with weak forces between the cages, so they're soft. Nanotubes, on the other hand, are strong and conduct along their length. Their large surface area and hollow structure make them genuinely useful in drug delivery, as catalysts, and across nanotechnology. Let's explain carefully why graphite conducts but diamond doesn't, given both are pure carbon. In diamond, each carbon uses all 4 of its outer electrons in covalent bonds, so no electrons are left free, and with no charge able to flow, it's an insulator. In graphite, each carbon bonds to only 3 others, which leaves the 4th outer electron per atom delocalized. Those mobile electrons drift when a voltage is applied, and that flow is conduction. So it comes down to this. Diamond has no free electrons. Graphite has 1 delocalized electron per atom to carry the current. A few final terms. Macromolecular means a giant covalent network of many atoms. Malleable means it can be hammered or bent into shape. Ductile means it can be drawn out into a wire. Sublimation is a solid turning directly into a gas, and a fullerene is a carbon allotrope of cages or tubes, such as C60. Let's turn all this into practical thinking. Need a hard cutting edge? Reach for diamond, a rigid giant covalent structure. Need a conductor that also lubricates? Graphite. Need a strong, light conducting sheet? Graphene. Need a wire, a metal, ductile with delocalized electrons. Need a low boiling gas, a simple molecular substance. In every case, the question to ask is the same. How are the particles bonded and arranged? Let's check your understanding one more time. First, state how many other carbons each atom bonds to in diamond and in graphite. Second, explain why fullerene C60 is soft despite having strong covalent bonds. And third, which structure would you choose for an electrode and why? Work those through.
One final set to test yourself on. A 10-ohm resistor carries 3 amperes, so find the power dissipated using power equals current squared times resistance. A 2 kilowatt heater runs for 30 minutes, so how much energy in joules does it use? And can you explain, in energy terms, the difference between a motor and a generator? Work those through and you'll have this outcome well in hand.
Let's finish with a check of your radian work. Convert 90 degrees into radians as a multiple of pi. State the exact value of cosine pi over 6. A sector has radius 10 centimeters and an angle of 0.8 radians, so find the arc length. And explain why theta must be in radians before using s equals r theta or a half r squared theta.